My name is Edwin Cardenas, and this is my Lab 4 Magnetic Field Bar Magnet presentation. Intro. The goals are to find how changing the orientation and distance of a magnet from an observation location affects the strength of exerted magnetic fields. The results were the magnetic moment equaled 1.25 amperes, and the exponent in I know it's not actually in, it's just the closest I could find, equals negative 3.5028. The fundamental principles, the first are magnetic fields. There's a concept, which, it's just moving charge around a magnetic force, which acts on other moving charges, and it's represented by vector B. With the force, of course, being given by F equals QV times B. Then there's the Biot-Savart law, which is just how you kind of find the magnetic field. It relates to current element the magnetic field produces, dB equals KMI dl times F over R squared. And it shows the magnetic field strength and direction. The magnetic field superposition, as Biot essentially just says that the total magnetic field is equal to the sum of all of its individual fields, and it just lets us calculate it easier. And finally, magnetic dipoles, which are a current loop that produces a magnetic moment, M equals IA, and its field patterns resemble a tiny bar magnet. So that's pretty neat. The lab steps. This is us doing the lab right now. So first, we opened the magnetometer app, and then we placed the phone flat, rotate until the exponent of the magnet field is near 0. And then we were able to go into the other step. Then we aligned the meter stick and bar magnet along with the phone's bottom edge until, of course, they went east-west. Then we moved our phone to find where Bx is largest, By is smallest. We jotted that down. We kept the phone flat and orientated it while measuring the x component of the magnetic field distance given. Bx equals 20, 70, 120, 170, and 220, taking 3 readings for each. We entered all the measurements in the Excel spreadsheet, and we plotted them. And for the off-axis, we found a perpendicular, so B net equals 100 moment t, and record this as d perp along with the Earth's By value. We measured then the x, y, and z components at that location, correcting B for y for the Earth's field. And then finally, also we don't need the Excel stuff. And then we compared their experimental and theoretical results, and then made the video. Here are said results. As you can see, it did get, it went down in relation. It's just, it's not really much to speak of, honestly. Here are some of the observations. Now, I'm gonna be real. There were some sources of error. First, we were doing it we were on the table. We realized it actually had like a little bit of metal. So there's a decent chance they did kind of distort the magnetic field a little bit. There's also a good chance the phone was just kind of like misaligned, which could mess it up. Also, I forgot who did it, but I don't remember if what they calibrated it to, so that could also just be a source error. The observations where the magnitude of the magnetic field decreases as the distance from the bar magnet increases. The x component of the field is strongest when the sensor is directly in line with the magnet's axis and weakens off-axis. And finally, when measuring off-axis, the y and z components become more significant, showing how the magnetic field changes direction around the magnet. Then the code, of course. Yeah, like I said, there's not really much to speak of here. The right-hand side is in front. I'm just kind of like starting it off and just defining anything. And of course making like the picture of the magnet. And these are the, these are going to be the arrows, with the B scale being the scale of the arrows. Here's some more. It's just more, it just makes more of the arrows. And here are the results. As you can see, as it goes like away, it gets larger, and vice versa. And it just kind of proves it, right? So here, some of the questions we have to answer. So what are the effects of misalignment with the magnetic north? If the experiment had not been aligned with the magnetic north, and the meter stick were placed at an intermediate angle, the Earth's magnetic field would interfere with the bar magnet's field. This misalignment would cause the measured X component to include part of the Earth's field, leading to inconsistencies and inaccurate readings that vary depending on direction. As a result, the relationship between magnetic field strength and distance would no longer show a clear power law trend, and its calculated exponent in would likely be incorrect. And finally, the effects of combining two magnets end to end. Two identical magnets were stuck into an individual magnets, and the magnets would have been about twice the magnetic moment, producing a stronger magnetic field at all distances. Thank you for listening, and have a good day.